So here we are again, the equivalence point. Alright, so once again, we are adding strong acid to a weak base solution. We have 20 mL of the weak acid to begin with an initial concentration of 0.1 molar. To reach the equivalence point, you have to add enough volume of the titrant, in this case the strong acid, such that the number of millimoles are the same for both of the reactants, right? So when this happens and you apply your mice table, you're going to subtract 2 millimoles from both reactants and you're going to add 2 millimoles to the product. And ultimately what that means is that you don't have any reactants left. This goes to completion, so all you have now is 2 millimoles of the conjugate acid. Because you no longer have conjugate base present, this is not a buffer. And because this is not a buffer, that means they're going to have to switch over back to an ice table. So yes, in fact, the ice table we're going to be using relies on the fact that all we have left in here is the conjugate acid. But in addition to the conjugate acid, we also have water. So we're going to have the conjugate acid reacting with water to generate its conjugate base and hydronium. So yes, this is the acid dissociation. So conjugate acid plus base generates conjugate base plus hydronium. And this is your typical Ka dissociation equation, your acid dissociation equation. So we're going to have to switch over back to concentration units because we have to use an ice table, right? So the 2 millimoles of conjugate acid, which is all we have right now, we don't have any conjugate base and we don't have any hydronium. We're going to have to divide 2 millimoles by a total volume of 20 plus 4, so 24 mLs. And dividing 2 by 24 is the same thing as 0.0833 molar concentration. That's the initial concentration of the conjugate acid. As of now, we don't have any conjugate base or any hydronium. And the change needs to be applied based on the mice table. So sorry, my gerbil friends, but now we need to ice it up. So we're going to now apply the change in terms of x. So 0.0833, subtract x from that. The conjugate base and hydronium are the product, so add x to both of them. So the equilibrium concentrations will be 0.0833 minus x, x, and x. Alright, now, much like the example we did in the previous lecture, you have to recall that because we have run out of conjugate base and all we have is conjugate acid, by default the equation we have here is the acid dissociation equation. So we have to use the Ka value. What we have given is the Kb, which means that we need to convert the pKb to pKa by subtracting it from 14. And then we take the anti-logs of 10 to the negative 11.12 to get to the Ka. You need to have this value because without this value, whatever calculation you make is going to be wrong. And just keep an eye out on what it is that you have left. This is the conjugate acid, so you better have the Ka for the equation. Alright, so we use the equilibrium expression to come up with the proportions. So we have x times x, or x squared on top. On the bottom we have 0.0833 minus x. And if you divide 0.0833 by 10 to the negative 12, you're going to end up with a value that is roughly in the vicinity of 10 to 100 billion, which needless to say is a lot greater than 400. So that tells us the minus x is actually going to be negligible. So we get rid of the minus x, multiply 7.59 times 10 to the negative 12 by 0.0833. That's going to equal the new value of x squared. Take the square root of that value. That will give you the value of x. And looking at the table, the value of x corresponds to the hydronium concentration. So all you need to do now is take the negative log of it, and that will give you the pH. And because this is the equivalence point, and this is the equivalence point of a weak base with a strong acid, we were expecting to get a pH less than 7, and sure enough, the pH we got is in fact less than 7. So that's one way to check out and make sure that your calculations are making sense. If you get a pH that is greater than 7 for a weak base titrated with a strong acid, you did something wrong. Very likely, you forgot to change the Kb to Ka. Alright, now, in terms of the visualization, right, the pH is 6.10 at the equivalence point, or at least that's what we expect. So if we look between 6 and 7, 6.10, I would say that methyl red looks pretty promising in terms of giving you the proper visualization aid to be accurate as to when that equivalence point is reached. But you could also use areochrome black tea. That looks okay in terms of the calculations, and I'm even putting bromophenol blue, even though that one might be a little less accurate than the first two that I mentioned. And yes, right here I'm just showing you the structure of bromocresol green and methyl red just for your reference. All right, now let's do one more calculation. The calculation when we go past the equivalence point. So now we're going to be adding 5 mLs worth of material. So instead of adding the 4 mLs, now we go past it, right? The 4 mLs was the equivalence point. Now we have more amount of H plus added. So we have now added a total of 2.5 millimoles, and we know that by multiplying 0.5 molar by 5 mLs. Creating the MICE table, the least amount of millimoles is actually the amount of the base. So we're going to subtract 2 from both, and we're going to add 2 to the product. And so what that means is that you will run out of conjugate base, but you will have 0.5 millimoles of H plus remaining. All right, so because this is no longer a buffer, as a result of the fact that you no longer have a base present, you have to start with a conjugate acid, set up your acid-base dissociation equation. The conjugate acid is your new reactant, the conjugate base is your new product, and hydronium is also your new product. If you change the millimoles to concentration divided by the total volume, which is 25 mLs, this will give you the new initial concentrations for the conjugate acid and hydronium. The changes in concentration will be minus x, and plus x, meaning that your equilibrium concentrations will be 0.08 minus x, and 0.02 plus x, respectively. Inputting all of these values in your equilibrium expression, and remembering that this is the acid dissociation, implying that you have to use the value of the Ka, you have x times 0.02 plus x divided by 0.08 minus x. 0.02 divided by the value of the Ka, or 0.08 divided by the value of the Ka, yield values that are way higher than 400. So the plus x and minus x can be discarded. The only one that is kept is the x that's being multiplied. So you have 0.02x divided by 0.08x. So if you solve for x, multiply the 7.59 times 10 to the negative 12 by 0.08, press enter. Divided by 0.02, press enter. You should find out that x equals 3.04 times 10 to the negative 11x. And don't make the mistake of just taking the negative log of that. Look back at your ICE table and realize that the hydronium concentration is actually 0.02 plus x. And needless to say, 10 to the negative 11 is so much smaller than 0.02 that technically speaking, the hydronium concentration is just 0.02. So if you just take the negative log of the concentration, the excess concentration of hydronium, and just that, you will automatically get the pH of the solution. So you could actually bypass performing the ICE table for this particular section of the titration curve, concentrate entirely on the excess concentration of hydronium left over, and use that and only that to get the pH of the solution. And at this point, yes, we are very low in pH because we have gone past the buffer region, past the equivalence point. Now all we have is just excess H plus that's floating around. Okay, that does it in terms of the equivalence point and the past equivalence point regions of the spectrum of the titration curve. In the next video, I'm going to show you what happens with acids that have more than one acidic H, the polyprotic acids.